A thermochemical equation can give us a lot of information about what heat energy is gained or lost in a chemical process. For instance, if we have an equation AB goes to A plus B, and let's just pretend there's a 2 down here and a 2 here, and the enthalpy change for that reaction is positive 100 kilojoules, we could say for every 1 mole of AB that's dissociated or broken up, you'd have to input 100 kilojoules. For every 2 moles of B that's formed, you would have 100 kilojoules needed to be put into AB to make that happen. Remember, the positive or negativeness right here tells you whether something is endothermic or exothermic. In this case, it's endothermic. And remember that the coefficients, the 1 here, the 1 here, and the 2 here, tells you how much energy would be gained or lost per mole of reactant or product. Using thermochemical equations is what's talked about in example problem 5.4, and we'll work several problems that use thermochemical equations to help us determine how much of heat is gained or lost by a substance. Question number 1 says, how much heat is released when 4.5 grams of methane gas is burned in a constant pressure system? And it doesn't say it on here, but we're supposed to use the equation from question from equation 5.18, which is actually on the page right before, and that has CH4 plus O2 goes to CO2 plus H2O, and the enthalpy change for this, is a negative 890 kilojoules, or kJ. And to balance this equation, I need a 2 right here and a 2 in front of the H2O right here. Okay, and it asks, how much energy is released when 4.5 grams of methane gas is burned? Well, when looking at the thermochemical equation, we know if 1 mole of methane gas is burned, 890 kilojoules is released. But now it's not asking in the question if 1 mole is burned, it says if 4.5 grams of CH4 is burned. So we can use this just like we used in stoichiometry, where we can take and we can convert from grams to moles. And in 1 mole of CH4, in 1 mole of CH4 there are 16 grams, because carbon is 12, hydrogen is 4, and if you add that together, that's 16. So this calculation right here would give you the moles of methane. And then you can use the thermochemical equation relationship, where there are 890 kilojoules released for every 1 mole of methane that's burned. And so we can put our moles of CH4 here on the bottom. This is moles of CH4 up here in a position where it's going to cancel. And then our heat in kilojoules up here on the top. And for every 1 mole, which is right here, 1, there are negative 890 kilojoules released. And if we take 4.5 divided by 16 times negative 890 kilojoules that are released, we'll find out that there are 250 kilojoules of energy released in this process. So you see how a thermochemical equation with the delta H, or the change in enthalpy given as in the equation, can help us relate to the coefficients. In this case, the coefficient was 1 of one of the reactants. Let's look at a second example. Number 2 says hydrogen peroxide can decompose to water and oxygen by the following reaction. And notice it's a thermochemical equation because they give me the enthalpy change for this reaction as written in terms of moles. If 5 grams decomposes, 5 grams of H2O2 decomposes, how much energy is released? So same type of problem that we just did, except now we're starting with 5 grams of H2O2. And we need to convert that to moles. And in 1 mole of H2O2, we need to add up 2 oxygens, which is 32, plus 2 hydrogens, which is 34. It'd be 34 grams. And for every 1 mole of H2O2, I'm going to make an error, because what's the relationship between H2O2 and our enthalpy right here? Notice there's a 2 in front of the H2O2. For every 2 moles of H2O2, there are negative 196 kilojoules released. So see how this relationship right here comes from the balanced chemical equation, a 2 to negative 196 relationship. If I multiply this through, I should get negative 14.4 kilojoules or so that are released. when this process happens. A couple more questions about thermochemical equations. How are the energy changes of the system and its surrounding related? First of all, if energy is released, in other words, the energy is given off, so I'll call it a negative delta H, then released by the system, then it must be gained by the surroundings. And this brings up an interesting point, which is known as the First Law of Thermodynamics. And the First Law of Thermodynamics says that energy can't be created nor destroyed. It can just be transferred from one thing to another. So there's a transfer of energy from the system to the surroundings, or you could say from the surroundings to the system if it was the opposite type of thing. And that's what the First Law of Thermodynamics says, is that heat is energy, heat energy in this case, is conserved. How do you calculate enthalpy for a chemical reaction? Well, one of the ways, and there are a number of them, but one of the ways is by using something called a calorimeter. And there's a number of problems and practical exercises in your book that use calorimeters to help you calculate the amount of heat gained or lost. In your book, on page 185, there's a picture of a coffee cup calorimeter. And in here, it's simply two styrofoam cups nested together, a stirrer, and a thermometer. And this simple apparatus is used to measure heat accompanying reactions that are at constant pressure. Since the cup is pretty much open to the atmosphere, as long as you're not going to do something that's super duper explosive and change the pressure in the room, you're going to be at constant pressure, and therefore you can calculate the enthalpy change of a reaction by using a simple coffee cup calorimeter like this. So before we do a calorimeter problem, we're going to come back to this one in just a little bit. Let's skip down here to page 189 and just use a couple of, you can give it some thought questions and relate thermochemical equations one more time, and then we'll come back and we'll do a couple of calorimeter problems using a calorimeter. First of all, what effect do changes have on the enthalpy of a reaction for reversing a reaction? Let's say we had a reaction that was A goes to B, and the enthalpy was negative 100 kilojoules. If I had the reaction B goes to A, what happens to the enthalpy? Well, the enthalpy of the reverse of the reaction is simply the opposite sign. In other words, now it becomes a positive 100 kilojoules when the reaction is reversed. What happens if I multiply the coefficients by 2? So using the same reaction, what happens if I put a 2 here and a 2 here? Now the reaction has 2's on both sides because I multiply the coefficients by 2. Well, now what I do with the enthalpy is I multiply the enthalpy by 2. Since I have twice as much stuff, I have twice as much enthalpy. So it'll be negative 200 kilojoules then for this process. That's what happens when you multiply or flip around a reaction. By the way, what would happen if I would multiply a reaction by a half? Well, if I do that, I'd have to take the enthalpy, of course, and multiply it by a half or cut it in half. So that answers the question about dividing things as well. Let's take a look at this question at the top of the next page. It's a calorimeter type question where it says, when a student mixes 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 to 27.5. Calculate the enthalpy change for the reaction, assuming that the calorimeter loses only a negligible quantity of heat. The total volume of the solution is 100 milliliters and the density is 1 gram per milliliter, and the specific heat is 4.184. So a couple things to learn here. First of all, enthalpy can be calculated using a calorimeter, assuming that Q, which is heat, is at constant pressure. So then we can say Q at constant pressure is equal to the enthalpy, and this is equal to the mass of the substance times what's called the specific heat of the substance times the change in temperature of the substance. Triangle, remember, means change, and T here stands for temperature. S stands for something called specific heat, and the specific heat capacity of a substance tells us how much energy it takes to raise the substance 1 degree Celsius. And M, of course, stands for mass. And the specific heat, of course, also assumes that there's a gram of the substance. And there's actually a table of different specific heats of a number of substances in your textbook on page 184. And if you take a look at the top of that page, you can see that they have about 10 substances or so listed with their specific heats in joules per gram Kelvin. Notice the units, joules per gram Kelvin. So, working this problem now, we're assuming that there's two things that are mixing together, each of which are 50 milliliters, and they add together to yield a total of 100 milliliters at a density of 1 gram per mole. And if we know that density is equal to mass divided by volume, and we know that the density is 1, and we know the volume is 100 milliliters, our mass is therefore 100 grams. So we have 100 grams of the substance. The specific heat, we're told in the question, is 4.184 right here. And the change in temperature goes from 21 to 27.5. And generally when we measure change in temperature, we do temperature final minus temperature initial. And in this case, the final temperature is 27.5 and the initial temperature is 21.0. So our change in temperature is about, 6.5 degrees or so, right? Or 6.5 degrees. So plugging these into our equation now, H, or enthalpy, is equal to mass, 100 grams, times our specific heat, 4.184 joules per gram degrees Celsius, and our change in temperature is 6.5 degrees C. Notice the degrees C change, the grams cancel with the grams, and we end up with joules. And so 100 times 4.184 times 6.5. Oh, I believe that turns out to be about 2700 joules, 2700 joules, I believe. And since it tells us that the temperature is increasing, remember the thermometer that's making the measuring is part of the surroundings, not the system. We would have to say that the system, the NaOH and the HCl right here, lost that heat. And so we would assign a negative sign to this, saying that enthalpy change was negative from the viewpoint of the system, because the energy was lost to the surroundings. Okay, the second question is about a large bed of rocks, and it says that they're used in heating a solar home, and assume that the specific heat of the rocks is 0.082 joules per gram Kelvin, and calculate the quantity of heat absorbed by 50 kilograms of rock if their temperature increases by 12 degrees Celsius. So we're going to calculate the quantity of heat, so we're going to assume it's at constant pressure because it's a bed of rocks outside, and this is equal to mass times specific heat times the change in temperature, and we're told that we have 50 kilograms, so 50 times 10 to the third grams of rocks, times the specific heat, which is 0.082 joules per gram Kelvin, times the change in temperature, which was 12. Now, is 12 Kelvin, the change, the same as Kelvin here? And the answer is yes, because Celsius and Kelvin are the same per degree, and so you can write it as that, even though this is written as 12 Celsius right here. The Kelvins cancel with the Kelvins, the grams cancel with grams, and you end up with your answer in joules. And so the quantity turns out to be 4.9 times 10 to the fifth joules of energy that are absorbed by the rock. And notice we give it a positive value now because the system, which is the rocks, have absorbed this amount of heat energy. Second question, what temperature change would these rocks undergo if they emitted 450 kilojoules of heat? So now we use the same equation, H equals mass times specific heat times the change in temperature. your heat is 450 kilojoules, so 450 times 10 to the third joules are equal to the mass of the rocks, and we're told that there are 50 kilograms of rocks, or 50 times 10 to the third joules of rocks, times the specific heat, and we were told in the question up above that the specific heat of the rocks was 0.082 joules per gram Kelvin. Notice I put everything into joules here so it would match with the units of the specific heat, and then the change in temperature is the thing that I would solve for. So algebraically solving for this, we would find out that there would be a delta T of about 11 degrees temperature change, and I can do that in Celsius or 11 Kelvin, because remember the change in Kelvin or the change in Celsius is exactly the same. And I would say that the change in this temperature right here would be energy that's lost by the rocks, and so I could put it as a negative sign there, because remember the rocks lost that temperature to something else. When we return in the next video cast, we'll look at another calorimeter problem, more than likely, and then we'll also look at the next step using a special type of calorimeter called a bomb calorimeter to determine the enthalpy change of different reactions.